I'm going to show you a graphic that I wrote in uh, Java, and in the course of that I'm going to use some terminology that we need to first sort of understand. So I've pulled up a few sentences from the Wikipedia regarding entropy. Entropy, it says, can be understood as a measure of disorder within a macroscopic system. The macroscopic system for my graphic will be a transparent cube, which you'll understand in just a moment. Now, in isolated systems, entropy never decreases, and such systems evolve toward thermodynamic equilibrium, which in my mind at least means maximum entropy or chaos. Unpredictable, let's say, spatial locations and relationships would not be able to be predicted. Its relationship to the larger cube, its relationship to the other things in that cube. So, the change in entropy of a system is determined by its initial and final states, and this applies whether the process is reversible or irreversible. Now, this will make a little bit more sense when you see the graphics. First of all, I'm going to show you the cube with 20,000 cubies, which are just simply tiny cubes of 2 pixels per side. And as you see it, you'll notice that, well, let me just show it to you and you'll see. That globe approaching us is composed of 20,000 cubies, little cubes, of 2 pixels each on a side. As it hits or collides with the 6 faces of the transparent cube, we are incidentally viewing this experience from the top of that transparent cube. Okay, these 20,000 cubies collide with the faces, the 6 faces of the cube, and as they bounce back, they form symmetrical patterns, which are clearly discernible. Okay, let me say that there is no friction of the cubies with each other. They are phantoms to each other, so they just go right through each other. And there are no collisions of cubies with other cubies. Now, there have been about 3 or 4 bounces so far against the faces, and we can still discern a little bit of pattern. But what I want to do now is to make this larger cube, this macro environment, rotate along its x-axis. It'll look like it's rotating backwards. So let me get that, and then I'll ask my questions. Okay, now the larger cube is rotating on its x-axis. I should have said earlier that each of the cubies is stationary. It does not rotate, so it keeps one of its 6 faces always toward the same face of the larger cube. And because each of the cube has 2 sides red, 2 sides green, and 2 sides blue, the effect will be that they will change color. Actually, they are simply being rotated with the larger macro environment. We can still see patterns. We can still see symmetry. Okay, but increasingly, as the bounces off the sides of the larger cube happen, there will be less and less symmetry that we can discern. We've now made one complete rotation. We're back to the red side here, and we can still see a little bit of pattern, okay? However, symmetrical patterns are becoming increasingly difficult to discern. So, now that you've got the idea, let me ask my 2 questions. If the graphics program were allowed to run indefinitely, would it eventually cycle back to symmetrical patterns that a human observer could discern? I think probably not. But there are no random variables in the algorithm, none. So theoretically at least, the exact location of each of the 20,000 cubies, that's by which I mean its spatial relationship to the larger cube and to every one of the other cubies, could be predicted, and it could be known. All right, now, out of that evolves this question about entropy. Since there are no random variables in the algorithm, does the entropy of the macro system, by which I mean the larger rotating transparent cube that contains all the other cubies, does that entropy increase, or do the spatial relationships of the 20,000 cubies simply become ever more complex, but never chaotic? And we've gone 5.5 minutes, so I will hope that you can answer my questions. Thank you.